Today we're going to get started on a new topic. It's going to be Earth structure. And not in terms of structural geology, faults and folds, but instead, what is the interior layers of the Earth and how do we define them? In our open geology textbook, this is section 2.2, and a lot of times I laud and praise our textbook, and this time I would say it is not exactly great, but it is going to be a resource for you. Now I just put in a picture of cake, and what in the world am I doing? We could define this cake in two different ways. We could talk about its chemical composition, how different parts of it are made of ice. The icing is made of butter and sugar. There's vanilla, there's flour, right? We could define the cake and the layers of this cake chemically. We could also define this cake by its structure, its behavior, the physical aspects of the smooth icing and the spongy sponge. We're gonna do the same thing today with planet Earth. So that was my fun analogy. So how do we know Earth structure? There's gonna be 4 different ways. It's gonna be, we can do it based on gravity measurements, on density measurements, on seismology, which is seismic waves, and then last, certainly not least, but maybe the less, we know more about the interior of our planet from geophysics, which is the application of physics to planet Earth using gravity, density, and seismic, than we do from the geology, mineralogy, geochemistry of actually collecting samples. Now, to start today, we're actually going to attack Earth structure from the perspective of its composition. Next class, we're going to do the exact same topic, but going after its physical structure. So, here we define Earth's interior using its chemical structure. And to a certain level, you have learned this before, these words of, let's see, we do crust, mantle, and core, where crust is the thin eggshell on the surface of our planet, then mantle is the meat of the interior that makes up most of the volume, and then there is the core. And those are the 3 layers of our chemical structure that we're going to get into today. So number 1 is crust. I want you to think of thin, brittle shell as what the crust of the Earth is. It is, of course, we can say much more about it. Much of the semester we've actually been talking about the crust of the Earth, from mountains down to valleys. And if you were to draw a picture of the Earth's crust, this would be the simplest thing you could probably draw and be accurate. Now let's have there be some water here, because what I want to differentiate in this quick sketch we're making of the crust is that there is continental crust, and that is our continents as we see our planet, and then there's also oceanic crust, and they are fundamentally different types of our thin brittle shell that covers the Earth's surface. Now okay, so we're going to go under crust, we'll go capital A, continental, all right, erase, continental crust. This is this material that we live on, that we have the most experience with. It is composed of our igneous rocks, our metamorphic rocks, and our sedimentary rocks. All of the silicate minerals, the carbonate minerals that we've been talking about that have silica and aluminum and oxygen, maybe CO3 2-, right? We've talked about this so far this semester. These are the minerals and elements that make up continental crust. It covers 40% of the surface of our planet, and this is the part that we live on. And on average, it's 30 to 40 kilometers thick. So in our drawing over here, I've actually maybe drawn a thicker part where sometimes the continental crust can get up to 70 kilometers thick at mountain ranges. And when you get to something that is a mountain range, I want you to picture the continental crust having a keel like a boat or an iceberg that floats isostatically on the mantle. And so here is our mountain range, and below every mountain range there is to balance it out, there's a keel that goes down into the mantle. The contact between the crust and the mantle is a thing called the Mohorovicic discontinuity. I'm just going to spell it as MOHO right here, and it represents this line, and then down below here this is our mantle. Now, that is our continental crust. What about the oceanic crust? It's much simpler, compositionally and structurally, because what I have ignored in this part of the drawing here is all the sediments and the folded rocks, the igneous intrusions that cut through it. We'll actually go a little deeper into the oceanic crust, and let's do this. Let's make a sketch of it here first. Here's the top of the ocean, and here is the seafloor. The first layer on the bottom of the seafloor is sediments. And we're going to ignore those for now. We've already talked about them. Those are like muds, and this might only be a meter thick, maybe a foot thick. Underneath the thin layer of sediments, there's a horizon of lavas. So we're going to do this. And this is like the general stratigraphy of oceanic crust. There's a series of lavas. We call them, they're either sheet flows of basalt or they're pillow lavas. I'm going to actually put some like little hump shapes because we're going to talk about pillow lavas later in the semester. Underneath the lavas, there's a series of, there's a structure, it's called sheeted dikes. And then underneath the layer, and what these are our conduits that took magma from the magma chamber to the seafloor where the lavas were in place. And then underneath that, there is gabbro, and the gabbro represents magma chambers. Now they're frozen, and then underneath the gabbro layer is the moho, and then the mantle. So that is the basic. Oh, I thought we were doing chemistry. Well, one thing we could say here is the lava to gabbro portion of the oceanic crust is basaltic. And basaltic means that it is Mg bonded with Si and then some iron probably as well. We call these rocks mafic. Oceanic crust, as opposed to continental crust, is that it is thin. It is on average 7 kilometers thick everywhere you go on Earth. Some places a little thicker, some places thinner, but 7 would be the number that I would want you to memorize. And it is this kind of low-lying area that then topographically that gets covered by seawater. All right, we've already talked about the composition here. It's basaltic. Another word we could put in for basaltic is mafic, and mafic, you could say like there's the M for magnesium, there's the F for iron, and then of course there's silica because it is silicates. So there's our oceanic and continental crusts. Now let's continue deeper. And we're doing this by chemistry, so in some ways the moho, and in fact we all just call it the moho because it's so hard to pronounce, Mohorovicic discontinuity. And this is a compositional change point where we go from basaltic composition rocks from the oceanic crust. Above it, we'll go basaltic. And below the Mohorovicic discontinuity, the division between the crust and mantle. That might be the best definition you could say for it. Below it is mantle rocks, which is peridotite. Peridotite is a, it's MgSi and O. That's the composition of the peridotite. So what is the moho? Okay, we call, am I getting too sloppy here? We call it the moho because it's too hard to pronounce. And the definition that I would want you to learn is that it is a compositional boundary. It is the compositional boundary between the crust and the mantle. There's a big change here in terms of the minerals present. And if the minerals change, then there is a change in those properties as well. Things like density and earthquake wave speed also change at this compositional boundary. And we should probably put that. Minerals change. And if minerals change, physics properties change. All right, now below the Mohorovicic, oh, easy. It is not easy for me to say, is the Earth's mantle. And we're going to treat the mantle compositionally as one big chunk. It ends up taking 84% of the Earth's volume. That's impressively large number. Compositionally, the mantle, for this class, I want you to learn that it is homogeneous peridotite. And to a higher level petrologist, that's going to start to be a little offensive, but it's peridotite is a name of a rock, and it is a rock that is composed of olivine, plus pyroxene mostly. And I know you've already learned olivine. I can introduce you to pyroxene today. Basically, both of these are MgSi and O, so magnesium silicates. There's other minerals like garnet, spinel, and plagioclase, but for the most part, it's these two that make up the mantle. As you go deeper and deeper, olivine will change to something that's a pseudomorph of olivine. Pyroxene will also change as well, but the composition stays the same. So we're just going to call it all peridotite rock. How do we know about the composition of the mantle? There's a few different ways, but the best way that we know about it is we can actually directly sample it through something called the xenolith. By xenoliths. And see this word xenolith? Xeno means foreign, lith means rock, and that's what these are. These are foreign chunks of mantle brought up to the Earth's surface by a volcano. Foreign rocks of the mantle brought to surface by magma / volcano, right? They're the same thing. So as a picture of what is a xenolith, here's about as good as I can do for you. And this also shows you a chunk of peridotite. So imagine a magma rising up through the Earth's mantle, and that fluid magma can rip off chunks. And this is one of those chunks of peridotite, where that greenish color, that lighter green, is olivine. The darker green might be pyroxene. And so this is what I want you to picture the mantle is. So do you get what I'm saying? I'm saying that the inside of the Earth is green. And that's not entirely true for all the different horizons. But one thing I really like about this picture is that this picture on this side is typically what is shown in classrooms. Like, what does it look like on the inside of the Earth? Well, if it's the temperature it is, things are going to be glowing. But if we cool down the interior, right, that's what it's saying right here. If we cool down the interior, what would actually the rocks look like? And notice how the upper mantle is this green color. And I would love for you to walk away from this class thinking that the mantle is green. Now, as peridotite changes with depth, the mineral structure changes, and then a lot of the lower mantle is brown. But this is what I'd like you to picture color-wise the interior of our Earth looks like. You can pause it here, in fact, to soak that in. That's a neat figure. All right, to wrap this up, let's now get to the Earth's core. The Earth's core has never been sampled, but we know actually quite a lot about it. It makes up about 1/2 of the radius of our planet. Not much of the volume because it's the smaller radius right inside the interior. But we know about the Earth's core from either meteorites or from earthquake waves. And what we've learned is that it is iron plus nickel plus other. And what we know is that about 80% of the Earth's core is iron, and then maybe 15% of the Earth's core is nickel, and these are mixed together. And then scientists today are still trying to figure out what that 5% other is. We can just call it an unknown. And for this class, if I were to ask you, what is the composition of the Earth's mantle? I would have you say to me, oh, it's an iron nickel. We understand this through matching earthquake waves. Because when earthquake waves move through a rock, they're going to move through at a certain velocity. That velocity is going to correspond with density. And then we can run experiments about this is how fast an earthquake wave moves through iron. This is how fast an earthquake moves through iron plus nickel. This is how fast an earthquake wave moves through peridotite. And by science, over decades, we've been able to match this iron-nickel composition to the speed of earthquake waves. But the way that I would like you to learn it in detail today is through meteorites as a proxy. And here's what's cool about meteorites. Meteorites reflect broken up planetary bodies. All right, we call these planets, we call these asteroids. And what we have found is that when a meteorite or when a planetary body cools down, it can either cool down as undifferentiated or differentiated. We on planet Earth live on a differentiated planet where, due to density, metals have gone down to the core, magnesium and iron make up a mantle, and then the light stuff goes to the crust. Some planetary bodies weren't big enough to have such differentiation, and they remain all mixed together. And so what we have found by sampling meteorites that have impacted our planet over the years is that there are 3 different types of meteorites that we find. We find a family of undifferentiated meteorites. All right, so undifferentiated means has not gone into layers. And we also find differentiated meteorites. And it's these differentiated ones that matter because a big amount of them are called iron-nickel meteorites. And we think that these represent the dense core of some planetary body that got smashed to oblivion, and we now see a fragment of it fall to Earth as an iron-nickel meteorite. That's what the inside of our planet looks like. Now, the undifferentiated meteorites fall as well. We call these chondrites. So chondrites. And they actually kind of look more like stones, and sometimes they're called stony meteorites. And they're a mixture of iron and nickel, but also silica and magnesium and aluminum. And they actually have the bulk composition of Earth. So when we sample an undifferentiated meteorite, we're thinking this is what all of Earth's composition is. And then when we sample a differentiated meteorite, we say, oh, this is iron nickel, just like the Earth's core. There's a family in between the two, which are in between, and they're called pallasites, and they're super beautiful. Pallasites. And they have iron plus nickel plus Mg plus Si, and they preserve this really pretty texture that people want to collect. All right, that's the best I can do on the Earth's interior as a composition.